Thank you, Warren, very much. So I'm going to introduce my graduate student, Jiayi Li. So she is a fourth-year graduate student in my lab. So actually, I know her quite a while. She started out as undergraduate student at University of Iowa when I was a faculty member there. And then she was actually a chemical engineering major. And then she took organic too with me. And it turned out that become one of her favorite subjects. And then she later asked me if she could join my lab and do some chemistry. And then when I decided to move to Wayne State in 2008, it's 2018, and then she followed me from University of Iowa to Wayne State. And she actually have multiple projects in my lab, and she one of the few people that he always come up with the new idea and the new things for the projects. So she works on two projects. The first project that she will talk today is design and development of heparinase inhibitor, and she learned how to do on the docking and find out the best target based on her docking result. And the project she talked today, some of the newest project in the lab that we got funded a couple of years ago to find the catalyst to control the stereoselective glycosylation. And as she learned the project more, basically she came up with the idea how to identify the reactive glycosyl intermediates, and she did that, and she find out the kinetic study, learn on her way to think about the rate order, the rate of the reaction is a first order, second order, or third order kinetics. And then recently she actually learned how to do on the DFT calculation by herself in consultant with my colleague here, Professor Bernie Schlegel. And today she will talk about her current project, and then the works are almost done, and think, within a month, we will publish the result that she got. Jiayi, you can go ahead and introduce yourself and start the presentation.
All right, thank you, Hien, for the nice introduction. And thank you, GlycoNet, for the invitation so that I can talk about my project publicly. So today I am going to talk about phenanthroline-catalyzed glycosylation, and we're mainly going to focus on the expansion of substrate scope and some investigation for the mechanism. So previously, we reported that the beta-phenanthroline can catalyze some glycosylation and give us alpha-1,2-cis glycoside. So we coupled this glycosyl bromide with the alcohol with catalytic amount of catalyst B-phen, and give us the net retention of a anomeric configuration, which is this alpha-1,2-cis glycoside. And in our paper, we showed many examples of decoupling with variety of sugars, and we also show the case where we can use the catalyst to perform gram scale reaction, and we're also using this catalyst to synthesize the octosaccharide. So after that point, we asked a question: is B-phen the best catalyst for our system? So with that question, we went back and do the catalytic screening, and besides phenanthroline, we also tried several different type of catalysts, such as pyridine base of catalyst, bipyridine, terpyridine, and even tertiary amine type of catalyst. And we found out that this phenanthroline backbone is actually very important for our glycosylations. And with that, we went on and synthesized more non-commercially available phenanthroline. And we found out that this piperidine substituted phenanthroline gave us the best result. It not only shortened the reaction time, but also we can conduct the reaction at room temperature. And this phen improved our yield and alpha selectivity for the glycosylation. And at the end, we were able to expand our substrate scope. So here are some examples of the advantages of using this piperidine substituted phenanthroline as catalyst. I will call it phen from this point. So in this model reaction where I have tetrabenzyl glucose bromide react with this primary alcohol under 15 mol% of catalyst, when we use a B-phen, we only get to 40% yield. and 15 to 1 alpha to beta selectivity. However, when we switch to N-phen, we can get up to a 77% yield, while our selectivity still maintains similar. So in this case of very hindered secondary alcohol with a 30 more % of catalyst at 50 degrees Celsius, when we use B-phen, we get 74% yield and alpha to beta 10 to 1 ratio. When we switch to N-phen, we can get up to 89% yield, and the selectivity is greater than 20 to 1 now. And in this case of fucose, we react with the serine under 50 more % of catalytic loading at room temperature. When we use B-phen, we can get 85% yield. However, the selectivity is only 6 to 1 alpha to beta. When we switch to N-phen, we can get almost 99% yield, and the selectivity bump up to 11 to 1. So next, we are also using this N-phen to perform chemoselective glycosylations by taking advantage of the difference in the nucleophilicity of the alcohol versus this hemiacetal. So in this case, we show examples of coupling of a primary alcohol and a secondary alcohol to a sugar moiety, and we get great yield and great selectivity at this point. And we were also able to use this N-phen to perform side-selective glycosylations for steroids. For example, in this case of dexamethasone, we're able to couple this primary alcohol to the glycosyl bromide at room temperature and get good yield and great selectivity. And at this case of estradiol, we have 2 secondary alcohol versus a phenol alcohol. And with 30 more % of N-phen at 50 degrees Celsius, this less hindered alcohol coupled to the sugar and give us the major products. And next, we also explore orthogonal glycosylation to see if we can actually minimize some steps in the total synthesis for carbohydrates. And we found out that this catalyst can also bear a fluoride and a thiophenol leaving group. And we were able to couple the alcohol to the glycosyl bromide and give great yield and great selectivity. So next we move on to the mechanism. So previously in our paper, we proposed that there are 2 roles for our phenanthroline catalyst. And one of the nitrogen in the phenanthroline is served as a nucleophile, while the other nitrogen of phenanthroline is served as a hydrogen bonding acceptor. So in our proposed mechanism, we have this phenanthroline displace the bromide in the SN2 fashion and give us this beta glycosyl phenanthrolinum intermediate. And this intermediate was detected by mass in the last paper. And also with this DFT calculation, it suggested that the second nitrogen is hydrogen bonded to the anomeric protons. So once we have this stabilized intermediate, we have the alcohol approaching the anomeric carbon from the axial position and displace this phenanthroline out and give us this alpha-1,2,6 glycoside. So overall, this double SN2 reaction actually gave us a net retention of this anomeric configurations. So the next question is, can we get a higher resolution of this glycosyl phenanthrolinum ion? So with that, the first thing we try, of course, is trying to get the crystal structure. Unfortunately, until this point, I was not able to successfully get a nice crystal for any X-ray diffraction. And so next, we're thinking about, can we see it in NMR? But with working on carbohydrates so many years, everybody knows that at the 3 to 5 ppm region is for the proton NMR is normally very crowded. However, for our system, we are using N-phen as catalyst, And the NFAN had a great symmetry, have a plane symmetry in the structure. And in NMR, proton NMR, we're only going to see 3 signals around the aromatic region. So once we have this a sugar coupled to our phenanthroline, the plane of symmetry will be lost immediately. Can we observe this aromatic region in the proton NMR to see if there's any change in our catalyst? So I went on and do this experiment. The first thing is I need to, I use this deuterated benzyl protecting group to pretty much mute the aromatic region for the benzyls protecting groups. And we can see this aromatic anomeric proton at around 6.5 ppm. And then next, as soon as I add the NFAN, we can see at around like the aromatic region, we can see the 3 signals for the NFANs, and especially on this singlet at around 8 ppm, that represents the symmetry of this phenanthroline. And after 30 minutes, we start to see a lot of new signals shows up around that phenanthroline aromatic region. And more importantly, there are no longer singlets in this new singlet, in this new signals. And actually, we're observing a lot of doublets around this region. Around this singlet region. So we next subject this solution to mass spec and detected the mass for the intermediate. And the next thing I do is, what if we add some nucleophile? Can we form some products to prove that if that is the intermediate that forms in the reaction? And the answer is yes. After 30 minutes, I start to see the product peaks shows on the NMR at around like 5 ppm. And in 5 hours, there are more products showing. And at the same time, these new signals are still appeared at around the aromatic region, showing that the catalytic cycle probably still undergoes. To sum up my NMR experiment, basically I used this glycosyl bromide and reacted with NFAN, and we were able to see new signals of the lost asymmetric phenanthroline, and we also detect the intermediate by mass. And then next, when we add into the nucleophile, we're able to form this disaccharide. And after 24 hours, I isolate the product with 81% yield and great selectivity. So next, in order to get a higher resolution for the intermediate, I bump up the catalyst amount to actually 1 equivalent. And I took a COSY and a ROSY, and here are the 2 intermediate structure that I propose. The first one is the 4C1 structure for 4C1 chair for the beta glycosyl phenanthroline, and the next one is by chair flip. We get this 1C4 conformation. And with those 2 conformation, I propose a new catalytic cycle where we have this phenanthroline react with the glycosyl bromide and give us this 4C1 chair conformation of a glycosyl phenanthroline intermediate. And by chair flipped, we actually get to a more reactive intermediate in a 1C4 conformation. And this more reactive intermediate leads us to the final product. So at the end, I would like to thank Hien for the guidance in my project, and also my current group member for giving me this friendly and dynamic lab environment. And special thanks for my former group members, Faye, Eric, and Sanyong, for giving me all the training in carbohydrate chemistry and NMRs. And I can take questions now.